This lecture on trigonometric identities is presented on behalf of the Independent Learning Center of SQU. My name is Gerald Wanjala. To begin with, let's consider the right-angled triangle shown here below, which has sides with length A, B, and C, and an included angle x. We define the cosine of x to be A divided by C. We define the sine of x to be B divided by C, and the tan of x is defined as the sine of x divided by the cos of x, which is B divided by A. Now, from sine square x plus cos square x equal to B over C square plus A over C square, which is equal to B square plus A square over C square. And since we know that from the triangle above that B square plus A square is equal to C square, then we have that sine square x plus cos square x can be written as C square over C square, which is equal to 1. So if you square the sine of x and square the cosine of x and you add, if x is an angle in quadrant 1, then we have that sum will give you 1. So we have that for an angle x in quadrant 1, we have sine square x plus cos square x is equal to 1. And so this leads to the identity sine square x plus cos square x is equal to 1 for angles in quadrant 1. This identity holds for all angles, whether in quadrant 1, 2, 3, or 4. So the identity sine square x plus cos square x is equal to 1 holds for all angles. So we have the following set of identities. The first one is sine square x plus cos square x is equal to 1. The second identity is tan square x plus 1 is equal to sec square x. We get this from the first identity by dividing both the left and the right hand sides by cos square x. So if we divide the left hand side by cos square x, we see that we have sine square x over cos square x. That will give you this tan square x over here. You divide cos square x by cos square x, you get this one over here. And when you divide the right hand side by cos square x, you have 1 over cos square x. And 1 over cos square x is sec square x, and that's the sec square x over here. Similarly, by dividing the left hand side and the right hand side of 1 by sine square x, we get the identity 1 plus cot square x is equal to cosec square x. So in the course of this lecture, we will be making use of the identities 1, 2, and 3. A trigonometric equation is called an identity if it holds for all values of the variable. For example, the trigonometric equation sine x minus cos x is equal to 0 is not a trigonometric identity, since the equation does not hold for x equal to pi. If x is equal to pi, then we see that sine x is equal to 0, cosine x is equal to minus 1, and therefore sine x minus cosine x will give you 0 minus 1, which is equal to 1, not 0. So this equation doesn't hold when x is equal to pi, and therefore it is not an identity. So to show that a given trigonometric equation is not an identity, just find one value for which the equation fails. Then conclude that the equation is not a trigonometric identity. In proving that a given trigonometric equation is an identity, we make use of the following guidelines. The first thing that one has to do is, given an equation, pick one of the sides, or either the left-hand side or the right-hand side of the equation. Then your goal is to transform that side. If you pick the left-hand side, your goal is to transform the left-hand side into the right-hand side. Or if you pick the right-hand side, then your goal is to transform the right-hand side into the left-hand side. How do you do this? The second thing you do is use the known identities, like the 3 that we have looked at above. So you combine algebra, use algebra and the known identities to change the side you have started with. So if you started with the left-hand side, simplify that side, use algebra to simplify that side, combine it with the identities, simplify that side, and see if you can transform it into the right-hand side. Then the last thing that can be done is, if you get stuck, then try to convert every function. Try to convert all the functions involved in terms of sines and cosines. This may also help. So let's look at a few examples. The example says, verify the identity 1 over sec x plus tan x plus 1 over sec x minus tan x is equal to 2 sec x. So here we look at the two sides, left hand side and the right hand side, and we look for one which looks more complicated than the other one. So in this case, the left hand side looks more complicated than the right hand side. So we are going to begin with the left hand side. Always try to begin with the side which looks more complicated than the other one. In this case, it is the left hand side, so we'll begin with the left hand side. So the left hand side is equal to 1 over sec x plus tan x plus 1 over sec x minus tan x. This can be written as follows. We put everything over the same denominator, which is sec x minus tan x times sec x plus tan x. So write this sum as, the numerator will be sec x minus tan x plus sec x plus tan x. Then the denominator will be sec x minus tan x times sec x plus tan x. The numerator simplifies to 2 sec x. The denominator simplifies to sec square x minus tan square x. To simplify the denominator, we use the formula for the difference of two squares. So the denominator becomes sec square x minus tan square x, and this simplifies to 2 sec x, which is the right hand side. We have used the fact here that tan square x plus 1 is equal to sec square x, one of the identities that we saw just a moment ago. From this identity, we see that if we take tan square x to the right hand side, then we have that 1 is equal to sec square x minus tan square x, and that is just this denominator over here. So this denominator over here is simply equal to 1, and so this is equal to 2 sec x, which is the right hand side. Example 2, verify the identity 1 minus cos x over sin x equal to sin x over 1 plus cos x. Now here we are going to begin from the right hand side. We have the term 1 plus cos x. So we look for a way of introducing a cos square so that we can use the identity sin square x plus cos square x is equal to 1. So since we have 1 plus cos x in the denominator, we know that if we multiply that by 1 minus cos x, then we get 1 minus cos square x. So that suggests that we are going to multiply both the numerator and the denominator by the term 1 minus cos x. So if we begin from the right hand side, we write it as sin x over 1 plus cos x. Then we write it as sin x over 1 plus cos x times 1 minus cos x over 1 minus cos x. The numerator becomes sin x times 1 minus cos x. We use the formula for the difference of two squares to write the denominator as 1 minus cos square x. And the numerator will be written as sin x times 1 minus cos x. The denominator will be written as sin square x. Here we have employed the identity sin square x plus cos square x is equal to 1, and that tells us that 1 minus cos square x is equal to sin square x. This 1 minus cos square x over here becomes sin square x. Okay, so then this eventually simplifies to the numerator becoming 1 minus cos x, and the denominator becomes sin x, which is actually the left hand side. So I have shown that the right hand side is equal to the left hand side. We have the following formulas. The first one is called the addition formula for sine. It is sin x plus y can be written as sin x cos y plus cos x sin y. Formula 2 is called the subtraction formula for sine. So we have here that sin x minus y can be written as sin x cos y minus cos x sin y. Formula number 3 is called the addition formula for cosine. So it says cosine x plus y can be written as cos x cos y minus sin x sin y. Formula number 4 is the subtraction formula for cosine. So it says cosine x minus y can be written as cos x cos y plus sin x sin y. Formula number 4 is called the addition formula for tan. So we have tan x plus y is tan x plus tan y divided by 1 minus tan x tan y. Formula 6 is the subtraction formula for tan. So we have tan x minus y is tan x minus tan y divided by 1 plus tan x tan y. Formula 7 is called the double angle formula for sine. It is derived from formula number 1. So if you set x to be equal to y in formula number 1, then you get sine x plus x, and that would be sine 2x. So that gives rise to the double angle formula for sine, which is sine 2x is equal to 2 sine x cos x. This is obtained from formula 1 by setting x equal to y. Similarly, by setting x equal to y in formula number 3, we get the double angle formula for cosine, and this one says that cosine 2x is equal to cos square x minus sine square x. Just let x equal to y in formula number 3, then that will give you formula number 8, which is called the double angle formula for cosine. So cos 2x is equal to cos square x minus sine square x. But using the identity sine square x plus cos square x is equal to 1, we see that cos square x can be written as 1 minus sine square x. And therefore, the double angle formula for cosine can be simplified to 1 minus 2 sine square x. We can also use the same identity sine square x plus cos square x to write sine square x as 1 minus cos square x. And then that leads to another expression for the double angle formula, and that will be 2 cos square x minus 1. So the double angle formula for cosine is cos 2x is equal to 1 minus 2 sine square x, and that can also be written as 2 cos square x minus 1. Lastly, we have what we call the double angle formula for tan, and this is tan 2x is equal to 2 tan x over 1 minus tan square x. This is obtained from formula number 5 by setting x equal to y. Let's look at an example here where we apply some of these formulas. Verified identity, tan x minus tan y is equal to sine x minus y divided by cos x cos y. So in this example, the right-hand side of the equation looks more complicated than the left-hand side, so we are going to begin from the right-hand side. So the right-hand side is equal to sine x minus y over cos x cos y. Now we apply this formula for sine x minus y at the numerator to get sine x cos y minus cos x sine y, and the denominator is cos x cos y. We separate these two. We write this as sine x cos y divided by cos x cos y minus cos x sine y divided by cos x cos y, and this simplifies to sine x cos x minus sine y cos y, and this is just tan x minus tan y, which is equal to the left-hand side. So the left-hand side is equal to the right-hand side. Example number 4. Evaluate the expression cos theta minus phi, given that sine theta is 4 over 5, cos phi is minus 4 over 13, and that theta is in quadrant 2 and phi is in quadrant 3. So using the identity sine square theta plus cos square theta is equal to 1, we can write cos square theta as cos square theta is equal to 1 minus sine square theta, and therefore cos theta is equal to plus or minus the square root of 1 minus sine square theta. Similarly, sine phi is equal to plus or minus the square root of 1 minus cos squared phi. Since theta lies in quadrant 2 and phi lies in quadrant 3, we see that the cosine of theta is negative and the sine of phi is also negative, so we pick the negative sign. So cos theta is minus the square root of 1 minus sine square theta, which is 1 minus the square root of 1 minus 16 over 25, and that will give you minus 3 over 5. Similarly, sine phi is minus 5 over 13. And therefore, cos theta minus phi, which can be written as cos theta cos phi plus sine theta sine phi is the same as minus 3 over 5 times minus 12 over 13 plus 4 over 5 times minus 5 over 13, and that will give you 16 over 65. So the cosine of theta minus phi is equal to 16 over 65. Example 5, evaluate tan 2 theta given that sine theta is equal to minus 3 over 5 and that theta is in quadrant 4. We know that since theta is in quadrant 4, then cos theta is positive. And therefore cos theta is given by cos theta is equal to the square root of 1 minus sine square theta. And since sine theta is minus 3 over 5, sine square theta will give you 9 over 25. And therefore cos theta is the square root of 1 minus 9 over 25. And that will give you 4 over 5. And we know that tan theta is sine theta over cos theta, and that will give you minus 3 over 4. And therefore tan 2 theta is equal to tan theta over 1 minus tan square theta using the double angle formula for tan. And this will be minus 3 over 2 divided by 1 minus 9 over 16. And that will give you minus 24 over 7. So tan 2 theta is minus 24 over 7. We have the following formulas which we call the half angle formulas, which can be derived from the double angle formula for cosine. Formula number 1 is called the half angle formula for sine, and is given by sine u over 2 is equal to plus or minus the square root of 1 minus cos u over 2. The half angle formula for cosine is cos u over 2 is equal to plus or minus the square root of 1 plus cos u over 2. And the half angle formula for tan is tan u over 2 is equal to 1 minus cos u over sine u, which can also be written as sine u over 1 plus cos u. Now, how does one choose when to use the plus or the minus sign? The plus or minus sign depends on the quadrant in which u over 2 lies. If u over 2 lies in quadrant 1, then you choose the plus sign for both sine u over 2 and cos u over 2. If u over 2 lies in quadrant 1, then we choose a plus sign for sine u over 2 and a plus sign for cos u over 2. If u over 2 lies in quadrant 2, then we choose a plus sign for sine u over 2 and a minus sign for cosine u over 2, and so on. Let's look at one more example here. Example 6. Find cos x over 2 given that sine x is 3 over 5 and that x is in quadrant 2. Now, using the identity cos square x plus sine square x is equal to 1, we can write cos x as minus the square root of 1 minus sine square x. Why minus? Because we know x is in quadrant 2, so the cosine is negative. So cos x is going to be given by minus the square root of 1 minus 9 over 25, and that will give you minus 4 over 5. So cos x is minus 4 over 5. Now, using the half angle formula for cosine, we have that cosine x over 2 is equal to the square root of 1 plus cos x over 2, and that will be the square root of 1 minus 4 over 5 divided by 2, and that will be 1 over the square root of 10. So cosine x over 2 is 1 over the square root of 10. We have chosen the plus sign because if x lies in quadrant 2, then x over 2 lies in quadrant 1, and therefore the cosine x over 2 is positive. So we choose the plus sign in this case.